Hi, in this video we're going to look at some basic conservation of momentum problems, and these ones come from Physics for You, which is a popular GCSE physics text. So let's have a look.
Question 3. A truck of mass 2 kilograms travels at 8 meters per second towards a stationary truck of mass 6 kilograms. After colliding, the trucks link and move off together. So this is a typical collision where it's all simplified down to the fact that there was one object moving before and they move off as a single object. They join and move off as a single object after the collision. So we've got one moving object and one static object before, and then they both move off together after. So it's the simplest way you can have this kind of collision. So the before situation is that this 2 kilogram truck is traveling towards this 6 kilogram truck, and the 6 kilogram truck isn't moving initially. So it comes in here, 2 kilograms traveling at 8 meters per second, and hits the second truck, which isn't initially moving. And what happens then is that after the collision, they have stuck together and are moving off with this new velocity, which I've called v3. Now, the conservation of momentum for this collision says that the total momentum before equals the total momentum after. So the momentum in the before situation equals the total momentum in the after situation. Now remember that it's a combined object moving after, and there was only this object moving before. So if we imagine this is M1 and this is V1, this is M2 and this is V2, and then this object is M3 and that's V3, we should be able to write an equation for that.
And the equation is simply M1V1 plus M2V2 equals M3V3. So all we've done here is turn the momentum of this into an item in our equation, and the momentum of this into an item in our equation, and the momentum of this combined object becomes an item in our equation. And the conservation of momentum says that the total momentum before, the sum of these two, will equal the total momentum after, which is this one. Now, it's important to remember that momentum is a vector quantity. This is a velocity and it has a direction, and this has a direction, and it won't always be obvious like this, that when this thing hits a stationary object that they're going to head off this way. It won't be as obvious as that in all circumstances. So even though this is an easy one, we start by reminding ourselves of some of the important issues here. So firstly, we need to decide on a direction to take to be positive, and I'm going to decide that this direction here to the right is positive. That means that the 8 meters per second is a plus 8, and that's the only thing we need to introduce at this point, the idea that to the right is positive and that 8 meters per second is a plus 8 to give it its direction. So M1 is 2 kilograms and V1 is plus 8 meters per second. So 2 kilograms times plus 8 meters per second is added to 6 kilograms times 0 meters per second. And that's equal to 8 kilograms times V3, because we don't know it yet. So we have 2 times plus 8, which is 16, 6 times 0, which is 0, and then 8 times V3. So we've got 16 plus 0 on one side and 8v3 on the other. We need to divide by 8. So 16 plus 0 over 8 equals v3, and that means v3 equals plus 2. So v3 equals 2 meters per second that way. And that's telling us that the final velocity of this combined object is 2 meters per second to the right. It came out to be positive, so we know that it's the same direction as our positive direction. If this had come out to be negative, that would have been telling us about it moving to the left. Question 4. In a sea battle, a cannonball of mass 30 kilograms was fired at 200 meters per second from a cannon of mass 3,000 kilograms. What was the recoil velocity of the gun? So what's happening here is we have a basic explosion. The cannonball is fired out in one direction and the cannon goes backwards in the other direction. So as I say, we describe this as an explosion. So we've got a cannonball going out the front at 200 meters per second and a cannon going back at some velocity that we don't know. Okay. So we want to draw this as a before and an after situation. So we have a cannon, and inside it there's a cannonball. And in the before situation, the cannon's sitting still and the cannonball's sitting still. They both have zero velocity, and so they have no momentum. Now in the after situation, we have a cannonball flying forward and a cannon flying backwards. Okay, so they start off together. One flies forward, one flies backwards. And it's this backward movement of the cannon that we're calling the recoil velocity. That's a term used for a weapon that comes backwards as it's fired. Recoil. Okay, so the cannonball goes forward, the cannon comes back, and it's this backward velocity of the cannon that we're trying to find. So it's important to establish straight away what direction you're going to be taking to be positive. Because we're going to have two directions in this answer. We're going to have forward and backwards, and I'm taking the forward to be positive. So when I use any velocities, if they're in the forward direction, I will give them a plus sign. Now in the problem, we do know that the cannonball is moving forward with 200 meters per second of velocity. So we need to put that detail on. So I've added some detail onto the diagram here. We've set both the velocities to 0 at the beginning. We've told ourselves that we have a mass 1 of 3,000 kilograms, that a mass 2 of 30 kilograms, and that afterwards the cannon has a V4 value that we don't know, and that the cannonball has a V3 value of plus 200 meters per second. So once again, conservation of momentum says that the total momentum before here equals the total momentum after. So what we're saying here is that M1 V1 added to M2 V2 equals M1 V4 added to m2 v3. So remember that that's just 3,000 times nothing added to 30 times nothing. There's no momentum on that side. And then we have (3,000) v4. And we're adding to that 30 times plus 200. So basically got 0 on this side, a big fat 0, because nothing was moving, equal to 3,000 v4 plus 30 times plus 200, which is 6,000. So we need to subtract 6,000 from both sides, and that gives us that minus 6,000 equals 3,000 v4. And now we need to divide both sides by 3,000. So we've got 6,000, minus 6,000 over 3,000 equals v4. And that tells us then that v4 equals minus 2 meters per second. And that minus is telling us that it points against the direction of the cannonball. So it's backwards compared to the cannonball, which we were expecting. So the cannon recoils at 2 meters per second when the ball goes forward at 200. That's that. Question 5. A heavy car A of mass 2,000 kilograms travelling at 10 meters per second has a head-on collision with a sports car B of mass 500 kilograms. If both cars stopped dead on colliding, what was the velocity of B? So this is interesting because they say stop dead. So if you think about it, you've got two moving objects at the beginning and both of them stopped at the end. So this is like the explosion being run backwards. The explosion has them both stationary at the beginning and both moving in opposite directions at the end. So this is like the explosion with time run backwards. So the objects are coming towards each other and end up stopped at the end. So it's going to work out very similar to the calculation for the explosion. So we have a before situation where these are travelling towards each other, and we have an after situation where they have hit each other and stopped moving. So they're travelling towards each other and they have momentum that causes either object to stop. What they must have here is equal and opposite momentum, because that's the only thing that will give us a final momentum over here of nothing. Because if both objects are stopped, the final momentum must have been nothing. And that means the sum of the initial values of momentum must also have been nothing. So if the positive momentum of the blue thing must have had the same value as the negative momentum of the red thing, because when they're added together we end up with 0 at the end. So again we need to decide on a direction to be positive. I'm going to just decide that to the right here is positive. So we'll just add some values here. This truck has a velocity v1. This one has a velocity v2. And over here, all the velocities on the other side, we're not going to have any momentum. There's no velocity in either object at the end, so the momentum over there is going to be 0. So let's just assume that everything on the far side is 0. So our equation is just going to be that m1 v1 plus m2 v2 equals nothing. And putting numbers into that, we have that 2000 times plus 10 for the velocity going to the right, added to 500 v2 for the velocity of the other one, is going to be equal to nothing because there's no momentum on the right hand side here because they're both stopped. So that gives us 20,000 plus 500 v2 equals 0. So we subtract 20,000 from both sides and we get that 500 v2 equals minus 20,000. And we divide them by 500. v2 equals minus 20,000 over 500 which is minus 40 meters per second. So what that's telling us is that the red object was travelling to the left at 40 meters per second before the collision. And that's what we were trying to find. Okay, it comes out to be minus because we took that way to be positive. And so the calculation recognizes that we put a plus number in here, and when we get our final answer, we get a negative, which tells us it points the opposite way. Okay. Question 6. A man wearing a bulletproof vest stands still on roller skates. The total mass is 80 kilograms. A bullet of mass 20 grams is fired at 400 meters per second. It is stopped by the vest and falls to the ground. What is then the velocity of the man? And how does this compare with what you see in films? So they have put the guy on roller skates so that he's free to move. What happens here is the bullet comes up to him, hits the bulletproof vest and falls to the ground. So all the momentum is now in the guy and he moves off like this. So that's what we have to represent here. So we put on the mass and velocity of the bullet and the before details of the guy. So we should straight away decide on a direction to be positive, and I'm going to take to the right to be positive. So at the end of this process, the bullet has stopped, and we're interested in figuring out what this final velocity of the guy is, this v4. So the conservation of momentum says that the total of the momentum before has to equal the total of the momentum after. So we can write an equation telling us what's going on there. So we've got m1 v1 added to m2 v2, and that's going to be equal to m1 is now travelling at speed v3, and we're adding that to m2, the guy, now travelling at speed v4. So these just need some numbers put in. So we've got 0.02 times 400 added to 80 kilograms times nothing, and that's equal to 0.02 times 0 added to 80 kilograms times v4. So there are two momentum values here that are nothing. That one's nothing and that one's nothing. So we need to do 0.02 times 400, and that's equal to 80 v4. Just need to also recognise that we were taking this 400 to be positive, so there is a direction thing in here. This points to the right. So 0.02 times 400 gives us 8 on this side, and that's equal to 80 v4. So v4 is going to be 8 over 80. And 8 over 80 is 0.1 of a meter per second, and it's a positive 0.1 meter per second, so the guy is moving to the right because that's the direction we took to be positive. Now the second part about, how does this compare with what you see in the movies? Well, when we see people being shot in movies, they often go flying across the room. 0.1 meter per second is not going to make you fly across the room, and that's really, I think, what they're getting at here. That movies exaggerate these things for dramatic effect rather than being accurate. Okay. Question 7. A Saturn V Moon rocket burns fuel at the rate of 13,000 kilograms in each second. The exhaust gases rush out at 2,500 meters per second. A. What is the change in momentum of the fuel each second? B. What is the thrust? And it says see also question 15 on page 141 if you've got the book. So here we have a beautiful picture of a Saturn V being launched. And what's going on here is that hot gas is being rushed out the back of this, and by throwing away large amounts of mass in one direction, the rocket is given momentum in the other direction. So how do we find the change of momentum? Well, we have a mass here of 13,000 kilograms, and it's taken from an initial speed of nothing and brought up to a final speed of 2,500 meters per second. So the change of momentum is going to be mv minus mu. And so we can find our change of momentum by multiplying our 13,000 by 2,500 and taking off the original momentum, which was nothing. So this 13,000 times 2,500 is our change of momentum. That gives us 32,500,000 kilogram meter per second of change of momentum. It says then, what is the thrust? Well, we also have an equation that says that the impulse Ft equals mv minus mu. So what we've got, that figure we've got, is mv minus over u. We can get the thrust by dividing mv minus mu by the time. And the time for this to happen was a second. This is how much mass was thrown out in 1 second. So we've got 32,500,000 over 1 second, which gives us a force of 32,500,000, and that's now in newtons. So 32.5 million newtons of thrust is how much we get from that. And that's it. Thanks for watching.